let's resume the class. Okay, so let's take a look of some variations of the permutation problem or the combination problem. Okay, so here, let us take a look of this word, SUCCESS. Okay, success. And then we want to make arrangement to them. But then you will see that, okay, so how can we arrange them? So this is an arrangement. So this is success. This is an arrangement. So we can make an arrangement like EU, CE, C, EU, CE, EU, C, there are too many E's, okay? EU, CS, CSS. So this is another arrangement, right? So we can make many arrangements to them. And how many are there? How many are there? So this is a permutation problem, right? But then some of the words here, some of the letters here, and they are repeating themselves. So S are repeating, C are repeating. So that makes the problem a little bit more complicated. So if we are looking at a more different example, so how many characters are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 characters. So if I ask a different question, so I have A, B, C, D, E, F, G. Okay, so I have A, B, C, D, E, F, G. How many different arrangements are there to arrange them? So we are making them more, taking them more. So how many ways are there? There should be. So for this one, the number of ways should be what? It should be 7 factorial, am I correct? Yeah, because you have 7 choice for the first characters, 6 choice for the next one, 5 choice for the next one, and so on and so forth. So this is 7 factorial. But this one, this is difficult. But let's try to use the same idea, okay, to make arrangement, to count the number of arrangements here. So to make everything simple, so let's consider all these S, they are different. So let's call this S1, this is S2, and this is S3, okay? So these S, we consider them different at the beginning. We will later make them the same. But now, at this point, let us consider them different. So we have 2C, let's call it C1, let's call it C2. Is that okay? So in that sense, if I have S1, U, C2, C1, E, S2, S3, we still consider them as different arrangement. So if this is the case, how many different arrangements are there? How many? How many? How many? I consider these two are different. I consider all the S's are different. So how many arrangements are there? How many? How many? All of them are different, right? 7 factorial. Okay, so if all of them are different, it means that we still have 7 factorial arrangements. Okay? But suddenly, there is some magic. Okay, it wipes out this 1 here and 2 here. So now the C's are now becoming the same. It's not different anymore. So previously, okay, so before the magic, it is C1, C2, C2, C1, right? We consider them as different. But now, when the label on the C disappear, then we will consider them to be the same. Am I correct? Now, if the label of C is gone, but the S's are still there, how many arrangements are there? So it's no longer 7 factorial, right? We are doing overcounting. So when we are overcounting, so let's look at this. We have SUCCESS, SUCCESS. These 2 cases are overcounted. These 2 cases are different before, but they should be counted as 1 afterwards. So what are the other cases? Let me give it an example. So for instance, you may have US1, S3, C1, E, S2, C2. This one will be overcounted with this case, U, S1, S3, C2, E, S2, C1. Am I correct? So previously, these 2 are different cases, but now they should be counted as 1. Okay. So can you see this? Every case that has C1, C2 here will have a corresponding case C2, C1, and they are overcounted. Okay. Okay, so here we have C1, C2 here. If you replace it by C2, C1, they are counted as different cases before, but they should be counted as the same one now. Okay, so we don't have 7 factorial if the labels on C is now removed. How many ways are there? So it should be 7 factorial divided by 2. Very good. Divided by 2. Is that okay? Good. So now this should be counted as the same. Okay. So now the two cases are merged. Let's do something more. Okay. Now we have what we are going to do. We are going to remove the labels on S as well, so that we get back to the original problem. So to remove the label of S, so we want to check out how many cases are overcounted. So originally we have S1, U, C, C, E, S2, S3, but we are also counting this like S1, U, C, C, E, S3, S2, right? When the S are different, then these are different. But when the S are the same, then these two should be the same. Am I correct? It's not here. It's not just these two cases. We also have something like S2, U, C, C, E, S1, S3. Am I correct? Is that okay? And there could be more. There could be more. So if you know how many different cases should be combined into one, then we know what we are going to divide it further. So how many? How many are there? 3 cases or 3 factorial? Okay. Any arrangements of these 3 S's, they should be merged, they should be combined into one. So it's not just 7 factorial divided by 2, it should be 7 factorial divided by 2 and then also divided by 3 factorial. Is that okay? Is that okay? So in general, it is like 7 factorial divided by 2 factorial and also 3 factorial. Okay, so this is the case. So we can use this, we can generalize this. So we can generalize this to even more difficult cases, like this word. So this is usually a magic word. So it's abracadabra. Okay. Okay. So difficult. Abracadabra or abracadabra or abracadabra. Okay. So usually this is the magic word that is used in a lot of the foreign children's storybook, like the Snow White, you have a witch, or wherever you have a witch, abracadabra. Okay, so something like this. So the same. Okay, so here we still want to ask how many different arrangements are there for this word. So let's first of all count the number of characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 characters here. And then how many A's? So A contains 1, 2, 3, 4, 5. 5 A's. How many B's? B, there are 2 B's, right? C, there is 1. D, there is 1. And then R. Okay, R, there are 2 of them. Let's add them up together. So it adds up to 11. Okay, so how many different ways of arrangement? So again, if everything are different, then there are 11 factorial ways. But then we have repeated A. So if we want to remove the repetition due to this A, we should divide this by 5 factorial. B appears 2 times. So if we want to remove the repetition due to B, we should divide this by 2 factorial. Is that okay? C appears 1 time. Okay, it doesn't make any difference, so we don't need to divide it. But if you like, you can divide it by 1 factorial. 1 factorial is still 1. Okay. D, 1 factorial is still 1. And R, it is 2 factorial. It is 2 factorial. Is that okay? Is that okay? So, okay. so recently when I logged into my Facebook, so there are lots of interesting jokes. Okay, so there is one. This is like this. So we just check in the internet. Okay. 哎，庭院嘛 Okay. So okay, so this is one of the line written by. Okay, just checked from the internet. I made the mistake, but this is one of the line in a poem by Ouyang Xiu. Okay, so in the joke it asks. Okay, in the IQ question it asks, what is the next sentence of this one? Anyone knows? Yes. Eh? Not exactly. No. Anyone? Okay, so what is the next one? 杨柳对烟嘛。对烟. Okay, so the correct official answer is 杨柳对烟. Okay, whatever, you can check. Okay, but of course in the joke it says how many combinations are there, how many permutations are there. So it is exactly. So how many permutations are there for this one? So it should be 7 factorial divided by 3 factorial. Okay, so this is it. Okay. Okay, let us do. Okay, so we have a. So we learned this. So we can come up with a more complicated example. So okay, so let's talk about Morse code. Maybe I'm spelling it wrongly. So Morse code is something that is used even nowadays to send signals, to transmit message using dots and dashes. Okay, so if you are a captain in a boat, you need to learn some Morse code to send SOS message. And in the old days when I was still a kid, we still use Morse code in what? In Telegram. Okay, so we don't have internet, of course. The telephone is also very expensive. Okay, so if you want to make an international call, it is very expensive. So at that time, people make Telegram. Okay, Telegram is you send a message by dot dot dot. Okay, so someone who is sending and someone who is listening, and then decode the message, and then get back to the original characters and sentences. Okay, so in a Morse code, so there are two forms. Signals, they can be dots. It is a short duration signal, and there are dashes. Okay, so this is a dash. It represents something that is long. Okay, so for the SOS message, it is dot dot dot. So it is 3 dots and then 3 dash and then 3 dots. This is what I can recall. Now this is a problem about this Morse code. So suppose that we now have 5 dashes. Okay, and then we have 8 dots that we can use. So first of all, we want to ask how many different ways we can arrange these things. So it should be simple, right? The number of ways to arrange 5 dashes and 8 dots is easy. We can plug into the same formula. It is going to be 13 factorial because there are 13 items here. And then we divide it by 5 factorial, and then we divide it by 8 factorial. Is that okay? So this is a simple, direct application of what we have learned. But now, let us make this problem a little bit more complicated. So we are not going to use all these 13 characters. We are going to we can only choose 7 symbols to use. So we still want to ask how many different arrangements are there? So perhaps for some reason you cannot send a very long message. You can only send 7 symbols. And then to send 7 symbols, and then it can only have at most 5 dashes and at most 8 dots. How many ways are there we can do? Yeah, how many ways we can do? So it looks like complicated because we cannot plug in a formula. So you cannot have something like what? 7 factorial divided by what? Divided by what? I don't know how many dashes are there. I don't know how many dots are there. So what are we going to divide? But if you think it more deeply, it is just a rule of sum case. We can divide it into different cases depending on the symbols that you are going to use. So for 7 symbols, you may be using 7 dots. You may be using 6 dots, 1 dash. Is that okay? You may be using 5 dots, 2 dash, 4 dots, 3 dash, 3 dots, 4 dash, 2 dots, 5 dash, and that's it. You cannot have 1 dot and 6 dash because there are not enough dash. And then for each of these cases, you know how many ways are there. How many ways are there? There is 1 way. How many? Well, 7 dots. The message consists of all dots, so you don't have any choice. 7 dots. There's just 1 way. How many ways to have 6 dots and 1 dash? So it is 7 factorial. It is 7 ways. So it is also, you can do this by 7 factorial divided by 6 factorial, which is equal to 7. Is that okay? And how many ways for 5 dots and 2 dash? It is easy. 7 factorial divided by 5 factorial, 2 factorial. Is that okay? You don't need to compute this. As long as you know this one, you know this one. And how do you get 1? 1 is actually equal to 7 factorial divided by 7 factorial. Is that okay? You list out every one of them and you add them up. This is the answer. Okay? So this is nothing special. The most special thing here is whether you can divide it into all these cases. This is usually the hardest part. Okay, but believe it. I believe in yourself. The more that you work on this kind of problem, then the easier that it becomes. It is just list them out case by case. Okay, okay. A small case is easier to solve than a big case. So list them out into small cases, and then you solve them one by one. Okay, and now we have a next question. This is very interesting. Okay, I think. So we have learned factorial. Okay, factorial. N factorial is n times n minus 1 times n minus 2 up to 1. And now, so consider a k which is a positive integer. Okay, and then let's look at these two numbers. One is k factorial, but not just k factorial to a power. This power is k minus 1 factorial. Is that okay? So this is the first number that we have. Now the second number is, we have k factorial. This is a number. And then you have a factorial here. Okay. Now, so now you have two very large numbers. Which one is larger? Which one is larger? Is this one larger or is this one larger? Well, it's difficult to tell. Okay. But let me ask. Okay, so I will tell you. Okay, I will tell you that this number is larger. This number is larger. What's more, this number can divide properly this number. So I'm claiming that if you have k factorial, k to the power factorial, this k factorial, if you divide this by k factorial to the power k minus 1 factorial, it is still a whole number. This is still an integer. Okay, now this is what I tell you, and you should not believe me. And then what I need you to do is to prove that when this one is divided by this one, we still get a whole number. Okay, how can we prove this? Using something that you have learned so far. Permutation, combination, arrangement with something that repeats itself. Okay, so let me tell you. If I close my eyes, I would say 7 factorial divided by 2 factorial, 3 factorial, 2 factorial. It is a whole number. Why? I didn't make any calculation so far. I just write it down. I'm saying that this has to be a whole number. This has to be an integer. It is not a fraction. Why? Or I can do something more fancy. Okay, so let's say I have 10 factorial divided by 5 factorial, 2 factorial, 3 factorial. I would say this is a whole number. This has to be an integer. Why? Why? Can you see this? This is 7 factorial divided by 2 factorial, 3 factorial, 2 factorial. This is a whole number. And the next one, 10 factorial divided by 5 factorial, 2 factorial, 3 factorial, this is a whole number. I can also say 100 factorial divided by 33 factorial, 20 factorial, 10 factorial. This is also a whole number. Why? If you know why, could you please raise your hand? Okay, good. Okay. The reason is that we can make a story. We can make a story about this number. So imagine you have 7 items. Let's say 3 of them are apples, 2 of them are oranges, and 2 of them are lemons. Okay, how many ways to arrange them? So it must be 7 factorial divided by 2 factorial, 3 factorial, 2 factorial, right? This is the number of ways to arrange them. And it has to be a whole number. Okay? And similarly, this one is like there are 10 people. 5 of them are from school A, 2 of them are from school B, and then 3 of them are from school C. Okay, how many ways are there to arrange them if we are only interested in the schools, not the particular person that we have? So in that case, it is 10 factorial divided by 5 factorial, 2 factorial, 3 factorial. Is that okay? And how about this one? 100 factorial divided by 33 factorial, 20 factorial, 10 factorial. Okay, so you have 100 items. 33 of them are bananas, 20 of them are lemons, 10 of them are oranges, 1 watermelon, 1 melon, 1 lychee, 1 longan, whatever. Okay, 1. Okay, all of these are 1. Okay, but there are 33 apples, there are 20 lemons, and there are 10 oranges. How many ways to arrange them? So this is this one. Is that okay? Good. Now, the same. Okay, so it looks very terrifying. It looks like a big number. But let's look at k factorial factorial. And the bottom one is what? It's k factorial to the power k minus 1 factorial. So let's don't write it down into the power form. Let's write it down into k factorial, k factorial, k factorial, k factorial, and so on and so forth, k factorial. Is that okay? So how many of them? So there are k minus 1 factorial of them. Okay? So how do you visualize that this one is still a whole number? You can imagine that altogether, you have a total of k factorial items. Okay? You have k factorial items. K of them are apples, k of them are oranges, k of them are lemons. You have many, many groups. And the last group, let's say k of them are watermelon. Okay? Every group, the size is of k. So how many groups are there? How many groups are there? There are, how many groups are there? So k factorial items, each group, there are exactly k things. So how many groups are there? So there are going to be k minus 1 factorial groups. Is that okay? Is that okay? You have k factorial items in total. Each group has k items. So that will be k minus 1 factorial groups. Is that okay? How many ways to arrange the items into a line? So it must be k factorial divided by k factorial, and then k factorial, and then k factorial, and so on and so forth. Is that okay? So this corresponds to the number of ways to arrange k factorial items of this special form. And it has to be a whole number. It has to be an integer. Okay, I find it very interesting, yes.